All right, so we're going to be talking about the derivative as a rate of change, and we're going to look at some examples. But first thing I want to point out is if we're talking about a position function, we're talking about the function s of t. If we are asked to find the velocity, what we need to do is find the derivative of the position function. We're going to call it s prime of t, and s prime of t is the velocity function. If you are asked to find the speed is the absolute value of velocity. So there it is, absolute value of v of t. Okay. The acceleration is the second derivative of position, or the first derivative of velocity, which gives us our function a of t, the acceleration. If I wanted to find the rate of change of acceleration, that actually also has a name. We call it the jerk. All right. That is the third derivative of the position function. That is the second derivative of velocity. That is the first derivative of the acceleration function. The jerk I will call j of t. Now, the fourth derivative, fifth derivative, sixth derivative, they also have names. Okay? So we're going to get to that in just a second, but let's talk about the jerk for a second. Think about if you're on a roller coaster, you know, that thing goes 0 to 60, you know, maybe really fast. What happens as you're sitting in that roller coaster? You jerk back. You're undergoing there the third derivative of your position. Okay? So that's why it's called the jerk. All right? Now the fourth, the fifth, and the sixth derivatives have names. All right? Now I'm not entirely sure how they're related to all of this particular motion and stuff like this, but in my class, traditionally what we've done in the past, when we talk about these derivatives and we get to this class day, we all have or partake in some treats, and we'll set somebody to make some treats for our class. And this is what we call the fourth, the fifth, and the sixth derivative. Snap, crackle, and as you might have guessed, pop. So we actually eat Rice Krispie treats on the day that we talk about this in class. If you're watching this online, I hope you have a Rice Krispie somewhere nearby. This video was not endorsed or promoted. I wasn't paid for any kind of sponsorship by Rice Krispies or Snap, Crackle, and Pop. But pretty interesting. This is legitimate. You can Google it online or something. But let's go ahead and take a look at some examples. In the first question here, we are asked to find the body's displacement. It says the function s equals f of t gives a position of a body moving on a coordinate line with s is in meters and t is in seconds. Displacement is basically the final minus the initial. So they want us to look specifically from 0 to 2. So what we're going to do is we're going to find displacement. All right, displacement. By saying, well, what's s of 2 minus s of 0? And that's not too bad. You're going to plug that in, okay? You're going to basically have 5 times 2 squared plus 3 times 2 plus 3 minus, then you plug in 0 into all of that. And that's not terribly difficult. You end up with 3, by the way, on the second part. So you end up with, if you do the math here, 4 times 5, 20, plus 6 plus 3, 29, minus 3, which is 26 meters. So that's how far you've traveled from 0 to 2 seconds, as you've traveled 26 meters. This is your displacement. All right? Now, the next part of the question says, find the average velocity. Well, that's equivalent to the slope. All right? That's the change in s over the change in time, t. So that's going to be s of 2 minus s of 0 divided by the change in time, which is going to be from 2 to 0, or 0 to 2, I should say. So we already calculated delta s. That was the displacement here. All right. So we're going to say 26 divided by 2, and we're going to get 13 meters per second. This right here is what we call the average velocity. Okay? So soak that in for a second. Pause if you'd like to, or rewind and review this. But we're going to move on to another example related to the definitions we talked about earlier. When we talked about speed, acceleration, and all that good stuff. So here's a good time to pause. Okay. In this example, we're given a function, position function s, and they want us to look at it over the interval from 0 to 2. They want us to find the speed, which is the absolute value of velocity, and the acceleration at the end of the time interval. So we're looking specifically when t equals 2. So we really only care in this case about the end of the time interval. So what we're going to do is we're going to pick t equals 2. All right, so let's go ahead and take a look at that. All right, first to find the speed, I need to find my s prime. So s prime, which is your velocity function, okay, velocity function. Ooh, sorry about that. I don't know what's going on. It's acting up. All right, the velocity function. There we go. All right, so that's the first derivative there. That's going to be 4t squared, so that becomes 8t plus 4. Okay, you drop the t there. 8t plus 4, that is the velocity function. All right, but we want the speed, so we're going to take the absolute value of the velocity function. And we're going to say absolute value then of 8t plus 4. Okay, we take a look at that there. And in order to do this, we're going to find the absolute value of the velocity at 2. All right, and we get 8 times 2 plus 4. And what does that look like? Uh-oh, let's get the eraser out. What does that look like? That's 16 plus 4, which is 20. And of course, the absolute value is just 20. So we get there 20 meters per second on the speed. If it was negative, of course, we would express it as positively. But not a big deal there. Remember that velocity is a vector quantity and speed is a scalar quantity. So that's why we represent speed with absolute value. Now to find the second derivative, s double prime, which is v prime of t, which is the rate of change of the velocity, which is the acceleration. We take the derivative one more time, and we're going to get 8, because we had 8t plus 4, so derivative of that is just 8. And so it's a constant acceleration. This means that my acceleration is 8 meters per second, or 8 meters per second squared. So that's what that looks like right there. Okay, so not terribly difficult. I think we have room for one more example. So let's go ahead and add in one more example. Okay, yet again another problem. We're asked to find the body's speed and acceleration at the end of the time interval. So we're just concerned with 2. Okay, we're just concerned with the value at 2. So we've got a position function s equal negative t cubed plus 7t squared minus 7t from 0 to 7. We're only concerned with 7. So we're going to find s prime, which is the velocity function v of t, which is going to be negative 3t squared plus 14t minus 7 when I take the derivative. And then I know that I need to take the absolute value of that. Okay, so I'm going to take the absolute value and I'm going to plug in 7. All right, so let's see what we get there. Absolute value, negative 3 times 7 squared plus 14 times 7 rather. There we go. Hold on one second. Minus 7. All right, there we go. Something like that. Okay, and so we do all of this work here, and you can do that on your calculator. You get something like negative 56, I believe. All right, but the absolute value of that is 56. So our speed is 56 meters per second. Okay, so this is the speed. The velocity, however, would be negative 56. So just kind of keep that in mind. Remember, velocity is vector, speed, scalar. All right, now we're going to take the derivative one more time. S double prime, which is v prime of t, which is the acceleration function. And when I do that, I get negative 6t plus 14. Okay, that's not too bad. All right. Now what we're going to do is, since we've got the acceleration function, we're going to find the acceleration at 7 seconds. All right. We plug that in. Negative 6 times 7 plus 14. We get negative 42 plus 14. And we end up with something like negative 28 meters per second, or meters per second squared as an acceleration. So what does this mean? It means that it is actually decelerating. The function, or the position, the object that's in motion is decelerating. Okay? It's decelerating. So we might predict that after 7 seconds, the speed will actually be slower. All right? So just something to consider, but really some really good examples on how we can apply higher order derivatives to particle motion. And physics really deals with a lot of this stuff. So definitely great applications for calculus here. I hope this video was helpful, and as always, like and subscribe.